Hi, we're back in the control room of the 32-inch at Junk Bond Observatory, and I thought I'd address some of the questions that were asked about the last video that I posted. So bear with me here. I'm going to shift between the questions and the answers. Okay, EKZept, I hope I'm pronouncing that right. Is it EKZept or EKZept? Asks, can you put up some links to sample SCP code to illustrate what it looks like? Well, it's ACP, Alpha Charlie Papa, and you should be able to scare that up on the internet. You can download a sample copy, and there are a bunch of sample scripts and higher level things that the source code is available that you can take a look at. So I would recommend doing that. It's at dc3.com if you have any trouble finding it. What is ACP written in? I suppose that ACP is probably written in one of the C programming languages, but I don't actually know because I don't write ACP. I write software that interfaces with ACP to do things to the telescope. Let's go on here. What kinds of feedback do you get from the telescope? Well, we get position, we get what is it doing, is it currently slewing, is it currently tracking an object, is it parked, put in its parked position for bedtime during the day. We get, I don't know, all kinds of information potentially. That's mostly the information that we actually use though. For example, can you monitor the amperage on the drive motors and help detect stalls with that? Maybe. I don't know. I don't really feel a need to do that because the low-level control system that we're using, which is PCTCS by Dave Harvey, ComSoft is the company that makes it, and that's what you see on the screen behind me here. That's been a very reliable system. We have had no stalls. The system, the low-level system, is already error aware and handles a lot of that stuff on its own. Of course, it does communicate errors to the higher-level control system, and we can make use of that as well. But it's very rare for this telescope to have an error condition. What does your calibration sequence each night look like? Well, that's an excellent question. The observer comes out here and takes the dust cover off the telescope and starts up the script. The script, the script being the thing that I write. The script is actually two pieces of software. One is a real script that's interpreted at runtime, and it's written in VB script for this facility, although I have some facilities running a similar script in JavaScript. And the other half of my software is a big honkin' executable, which is basically just a bunch of class libraries that do useful tasks that are not done by other components of the system. Like it makes higher math available to the script, which doesn't have certain higher mathematics capabilities built in. It does coordinate transforms. It does, it converts motions and position angles of motions into RAs and decks at given times. It does all kinds of little housekeeping chores that really would be overkill to have in a script. So those are the two components. One of them is an executable. The other is an interpreted script interpreted at runtime. So the script slews the telescope to a location on the meridian that is midway between the east and west horizons and about 45 degrees above the horizon, so about halfway up to the the point directly above you. And it takes a very brief picture, I think about a 6-second picture, and it looks at that picture, the script looks at that picture and analyzes it and determines, with the help of some of the other libraries that I'm using, where the telescope is pointed. Basically, there's a bunch of stars in this picture, and we have a rough idea of where the telescope should be pointing. So we look in a star catalog, and we match up the stars in the picture with the stars in the star catalog. And by that means, we synchronize the telescope with the sky. Then we go off and do our observing. We can observe in one of several modes. We can forego these pointing exposures entirely and just not do them. We can do one before every exposure if we feel like it, if the telescope maybe isn't a very reliable pointer. We can do one every so often, or we can monitor the data images, and when the telescope pointing begins to be in error above a certain threshold, then we can do one to resynchronize everything. And what we do will actually depend on what kind of target we're observing, how important perfectly accurate positioning is for the application, and so forth. After that, we go look at the target. We take a long exposure. Usually with asteroids, it's a long exposure. For main belt asteroids at this point, we're exposing between 6 and 10 minutes in order to maximize the signal-to-noise ratio on the asteroids that we're observing. With near-Earth asteroids, of course, they're moving a lot faster. Their apparent motion against the sky is a lot faster, so we take much shorter exposures for those. Sometimes 30 seconds, sometimes a couple minutes, but it's a lot shorter than we can get away with in the main belt. And basically, the telescope just does this over and over and over and over all night, and this is super boring to do manually, so it really helps to have an automated system do this for you. Of course, one of the new features that we're rolling out here is that we're taking some of the dead time that we normally have in the early evening right after sunset and the early morning right before sunrise, and we're using that to look for comets or low solar elongation objects, whatever they may be. We don't think that that's necessarily going to be that productive, but at least it gives the telescope something to do and a chance of doing some interesting science during some times of the night that just are not very productive normally. Okay, so at the end of the night, the telescope parks. It aims at the southern horizon and comes to a stop. It stops the tracking. And then we take calibration images. We take 9 dark frames at one exposure setting, pardon me, 9 more at a different exposure setting. So we have two different exposures, 18 frames in total. We can use that to scale. We can use all these dark frames to average and scale to the data images for the night. We also take bias frames, and we use night sky flats. So basically what that means is that we take images that the telescope has taken of star fields. We take 1,000 or 2,000 or 3,000 of them and we average them, and that gives us a beautiful, beautiful flat field, and we can use those to calibrate the images. And once those tasks are done, then the telescope turns off and goes to bed, and that's it for the night.